Our lesson on 3.5 for our Trig class is going to talk about velocities. And there's two different types of velocities that we're going to talk about. One's called linear velocity and one is called angular velocity. So, I'm just going to skim through this paragraph. The rate at which a rider is traveling around a wheel is what we call linear velocity. So if you were a bug stuck to the edge of a tire and you were rolling around the tire, the speed at which you were rolling along the edge of the tire would be your linear velocity. However, there's something else called angular velocity, and that would be the velocity of your central angle. So you can imagine that they're kind of related, and they are definitely related. The faster the angular velocity, the faster the linear velocity. And let's keep reading here. The central angle swept out by a rider traveling once around the wheel is 360 degrees, which is 2 pi radians. So if one trip would take 20 minutes, then the angular velocity would be, well, in 2 pi of a radian rotation-wise would take 20 minutes. So if we reduce that, we'd get pi over 10, and then we label it with radians per minute in that case. So first, let's talk about linear velocity. The formula that we're going to use for linear velocity is v equals s over t, and that's the same s that we saw back in the last section, which is arc length. So, a point on a circle travels 5 centimeters in 2 seconds. Find the linear velocity. So the 5 centimeters is his arc length in 2 seconds, and we get 2.5 centimeters per second. Now angular velocity, we're going to use, it looks like a W, but I think it's actually omega, it's a Greek letter. And you're going to take your central angle theta, which is in radians again, and divide it by time. And the label here is going to be radians per minute, or radians per second, or radians per hour, or whatever the rotation time is. So a point on a circle rotates through 3 pi over 4 radians, so there's your central angle, in 3 seconds. Give your angular velocity. So the angular velocity is your central angle, theta, divided by 3. And again, if you want to change that to a multiplication problem, you can. That would be 3 over 4 pi times 1/3, which when we reduce, we get pi over 4 radians per second. Now, technically in a real world problem, you would not leave your answers as pi over 4, you do a decimal, but just because I don't want to grab my calculator, I'm going to leave it as pi over 4. So next example is we're a bicycle wheel with a radius of 13 inches, so that's our radius, and it turns with an angular velocity of 3 radians per second. Find the distance traveled by a point on the bicycle tire in 1 minute. Well, the first thing we need to do is we need to figure out his central angle. So I'm going to do that by looking at my formula. W equals, or omega I should say, radians divided by time. So the angular velocity is 3, so I'm going to put a 3 here. I don't know my central angle, and the time is 1 minute. Now be careful, because the angular velocity was radians per second, we would have to convert this 1 minute to say 60 seconds. So multiplying by 60, you're going to get 180 radians. So that's our central angle. They want to know the distance. Well, the distance traveled is his arc length. So I'm going to go back to our formula. Our second goal here is to find arc length. I'm going to go back to our formula from the last section that said arc length is radius times the central angle. So S equals, radius was 13 inches, and then now our central angle is 180 radians. So that comes out to 2340, and then remember 13 was in inches, so that would be inches. Essentially what we did was we found the circumference of our bicycle wheel, and we calculated how many times it went around that bicycle wheel. That's what the central angle is really telling you. So as you have seen, there is a definite relationship between these two velocities because there's some common variables. So let's look at why they're related. Let's start with our formula, S equals r theta. And if I was going to take this formula and divide both sides of the equation by t, what I'd end up with, and I'm going to draw it over here, is S over t equals, I'm going to leave the r out in front, and I'm just going to make it look like the theta is being divided by t. Now think about equivalency here. S over t is the formula for velocity. If I go back right here, S over t is really angular, or linear velocity, excuse me. So that's really a, come on pen, uh-oh, freezing a little bit. So I'm going to replace S over t with a v, and then if my pen will work, there we go, maybe. Okay. V equals r, and then theta over t is really our angular velocity, omega. So this is another formula that we're going to be able to use. Now the good news is I'm not going to make you memorize these formulas. However, if you start thinking about why they work, they're a little easier to use. You get a better understanding of how to use them. On your formula sheet, it lists out all of these formulas. Sometimes it's hard to figure out which formula to use, so you have to really act like a scientist and look at what variables you are given. Okay, our next example is a phonograph. None of you probably know what this is. Looks like a record player, and it turns at 45 revolutions per minute. Okay, that's important. He's not the number that we're going to use in our calculations, but we're going to use him to find something. The distance from the center of the record to the edge is 3 inches, so that is our radius. And then find the angular velocity and the linear velocity. So let's start with this 45 rotations per minute. If every rotation is 2 pi radians, what I can do is I can take 45 and I can multiply it by 2 pi, and this will calculate my central angle theta. So I'm going to leave it in terms of pi again because I don't want to grab my calculator. But now my central angle is 90 pi. So, oh, per minute, excuse me. You know what? I did not label this the right thing. Back up. 45 was rotations per minute, which means it's related to our angular velocity, omega. Sorry about that. Then, if I want to find linear velocity, we have a bunch of formulas to choose from, but I think I'm going to use the formula that we just came up with, which was linear velocity is your radius times your central angle. So, let's see, our radius was 3 inches, and now we know our, not central angle, I need a nap, angular velocity. So radius times angular velocity would be 3 times 90 pi, and inches, radians per minute, if we think about how this is going to work out for us, the radians are going to cancel out, and we're going to come up with, let's see, 270 pi inches per minute, because remember it's linear velocity, or because this is a real world problem, probably would make more sense to write your answer as 848.2 inches per minute. Alright, example 6. This Ferris wheel is going to show up a whole bunch in this chapter. So this time we have a Ferris wheel that has a diameter of 250 feet, which if you think about what that means, we have a radius of 125 feet. And 1 revolution takes 20 minutes. So we're going to find the linear velocity, and we want our answer in miles per hour. That's an important clue. Okay, let's start with the fact that our radius is actually given to us in feet. So what we're going to have to do is calculate the radius in terms of miles. So 125 feet, if you think about doing dimensional analysis, you would divide by 5,280 feet to convert this to miles, and I actually didn't do this yet, so I'm going to grab my calculator. It's going to be a decimal, and that decimal is, now don't round off too much, 0.0237 miles. Okay, hold on to that number. We're going to need him in a second. Now, another issue is we want to answer miles per hour, so keep that in mind. 1 revolution takes 20 minutes. So, for my angular velocity, 1 revolution is 2 pi. And instead of dividing it by 20, because I don't want my answer in radians per minute, I'm going to need it in radians per hour. I got to convert 20 minutes to a fraction of an hour, and of course we all know that's 1/3 of an hour, so I'm just going to round to 0.333. And I'm actually going to go ahead and type that on my calculator. So our angular velocity is roughly 18.868 radians per hour. So now using our new formula, because we need to find linear velocity, we can take our radius times our central angle. So if I do that, my radius is, remember, 0.0237 miles times our central angle of, not central angle, my goodness, angular velocity. So 18.868. And of course we're going to get a decimal, and it's probably not going to be very pretty. Alright, hold on to your hats, kids. Your linear velocity is 0.447 miles per hour. You are not going very fast, and that's probably a good thing because you're on a Ferris wheel. Alright, there's another set of notes that says in addition to 3.5 notes. So linear velocity has to do with distances traveled in units such as feet per second, miles per hour, kilometers per minute. It can really be anything. We've been dealing with, and I'm not really sure whoever wrote this worksheet what they were looking for in this blank. I think they're looking for the word linear. Not real sure. But anyways, that means we want to know the amount of distance traveled over time in a circular motion. I don't really know what they were going for, but let's continue on. This formula, remember, is linear velocity. We already learned this on the last set of notes. We actually already did this. Oh no, it's similar to the problem we did. We're a bug stuck on a tire, and 5 minutes we traveled for 2 miles. So his linear velocity, remember, would be arc length, which is the 2 miles, divided by time, which is 5 minutes, and we end up with 0.4 miles per minute. The next set of problems is very similar. So linear velocity would be arc length divided by time. So decimal here would be appropriate, 1.5 feet per minute. Labels are so important in this section, as we saw in a problem a little bit ago where they wanted the answer in miles per hour and we had feet per minute, and that was not good, so we had to do a little conversion. Alright, this next example, 12 centimeters every 2 seconds, so that means we travel 6 centimeters per second. Now the next set of questions is kind of backwards. Remember, if its velocity is arc length divided by time, this particular problem wants you to find arc length. So if I solve that formula for S, it would be velocity times time. So miles per hour an hour, so I don't have to convert anything, but 45 times 1/2 gives us 22.5, and then arc length is distance, so miles. Miles per hour and seconds, so we need to do a little conversion on this one. 10 seconds, we would have to divide by, to convert it to hours, you have to divide by 3,600 seconds in 1 hour. So the time is really teeny tiny, 0.00278 hours. So now my arc length is velocity, which is 63 miles per hour, times 0.00278 hours. And when I type that in, I get 0.175 mile. I guess technically I could have converted the miles per hour to miles per second, but I don't think that would have been very fun. So looking down the page a little more. Where am I? You know what, I think I skipped a few questions. Interesting. Looks like we are on the back. So I'm going to try to fit in the questions that I accidentally skipped down here. When you look at number 13, they want us to find the angular velocity, and remember, angular velocity's formula is your central angle divided by time. So for number 13, our central angle looks like it's 2 pi over 3. And then instead of dividing by 5, I'm going to multiply it by 1/5, so I don't have to get my calculator out and think too hard. Actually, you know what, I probably will get my calculator out anyways. You can leave your answer as 2 pi over 15 radians per second, but again, real life applications, pi answers don't really make a lot of sense. You'll notice that when you check your homework in the binder, I left a lot of my answers in pi because when I did my homework, I did not have a calculator. So, sorry. Oops. Apparently we jumped to number 16. This time they tell you that the central angle is 24, I'm assuming radians, since they have no label, and then time is 6 minutes. So, your angular velocity is 24 over 6, which comes out to 4 radians, and then the label was minutes on the time, so radians per minute. And when you get to 24, this time they want you to find, oh, interesting. So on 24, they give us some clues. They tell us that our angular velocity is 2 radians per second. And then for our radius, they tell us it's 4 inches. And then for our time, they tell us it rotates for 5 seconds. So the first thing we need to find is our central angle. So I'm going to rearrange the central angle formula with angular velocity to say theta equals omega times t. So with that, I can do 2 radians per second times the 5 seconds. So it looks like our central angle is 10 radians. Now they want to know the distance, which is arc length. Remember that is theta times r. So it doesn't really matter the order in which we multiply. 4 inches times 10 radians gives us 40 inches. Alright. Oops, I did skip 27, but, oh, actually we better go back to 27. It's a little tricky. So omega is 15 radians per second. And then your radius of this wheel is 5 feet. And then this is the tricky part, if you don't notice it. T is 1 minute. So we have an issue with labels. So instead of saying that's 1 minute, I'm going to go ahead and convert that to 60 seconds. Because I'm going to forget. So, just like the last problem, we first had to find our central angle by doing omega times t. So 15 radians per second times the 60 seconds. Oh, I can't think anymore. Can you tell it's early? Is 900 radians. And then to find our arc length, it's your central angle times your radius. So 900 radians times our radius was 5 feet. So let's see, that'd be 4,500 feet. I hope they wanted their answer in feet. Right. Now onto the back of the page. Okay. Very important to know that theta must be in radians. If you have degrees, you need to do a little conversion, and you would do that by multiplying by pi over 180. So degrees multiplied by pi over 180 converts it to radians. Also remember that 1 revolution is the same thing as 2 pi radians. So sometimes they'll give you your central angle in terms of revolutions, and you need to think about converting that to radians. So how many radians are in 5 revolutions? Well, that would be 10 pi. Because it would be 5 times 2 pi. It's not a distance around unless a circle has a radius of 1. Because remember, normally the distance around would be arc length, and you'd take whatever your radian measurement is, which is your central angle, and multiply it by your radius. So if you happen to have a radius of 1, then this is your distance around your circle. The angular velocity associated with these rotations per minute. So first thing you need to do is find your central angle by taking the rotations per minute and multiplying them. Keep calling this wrong thing. Omega is your rotations per minute times the 2 pi radians. So it looks like our angular velocity is 40 pi, and then we should abbreviate with radians per minute for the label. So 7.2 rotations per minute times 2 pi radians gives us, I'm going to do a decimal on this one, 45.2 radians per minute. Okay, we've got a point on the circle with radius given, and they must define the linear velocity. So, linear velocity's formula that I'm going to be looking at for these problems is s divided by t. So v equals, uh-oh, we need a little bit of work here. Remember that your angular velocity is theta divided by t. So, oh, you know what? I have a better formula. What am I thinking? Remember, we derived this formula that said linear velocity is really r times omega. So let's just do that. So 2 times 5 gives me 10. And then we should label, let's see, it's inches per time is seconds. Now this problem's a little backwards. We're going to use the same formula, but this time they tell us the angular velocity is 8 centimeters per second, and the radius is 3, and they want us to find omega. So if I divide both sides by 3, a decimal would probably be a little better here. You get 2.67 roughly, and remember this is angular velocity, so it's radians, and then per our time frame is seconds. And let's see, 20 RPMs. This is kind of like our angular velocity, except we need to take the 20 rotations per minute and multiply it by 2 pi. So our angular velocity is really 40 pi radians per minute. So the radius this time is 1. Well, I guess that's really easy, because remember, if the radius is 1, then your linear velocity is just your angular velocity. So the answer is 40 pi. We should label it though. It is feet per, and then the time was minutes on this one. Again, decimals would be fine. Okay, a couple more and we're done. We have a mixer blade, so a big mix master we're looking at, and it extends out 3 inches from the center, so there's your radius. The blade is turning at 500 RPMs, so that is kind of like our angular velocity. They want our answer in careful feet per minute. So first thing I notice is that our radius is not really 3. 3 inches, we'd have to divide that by 12 to convert it to feet, and we'd get 0.25 feet. So now when I think about using, we gotta do a little conversion here. Our angular velocity is 500 rotations per minute times 2 pi, so that would be 1,000 pi radians per minute. So now when I want to find, let's see, what was it again? Linear velocity. I could take my radius, which is now in feet, times my angular velocity, and I get, let's see, I gotta recalculate this, because when I first keyed this, I forgot to convert to feet. I'm gonna do a decimal. Okay, 785.4 feet per minute. That's pretty fast. Alright, velocity of a diskette. So we're talking like a CD here. It's 5 inches. But it says later on that it's a 0.2 inches from the center. So that means your radius that we're really talking about is the 2 inches. 3,600 revolutions or rotations per minute. So to calculate your angular velocity, we need to multiply the 3,600 times the 2 pi, and that gives us 7,200 pi radians per minute. Oops, that doesn't look like anything. So first we're going to find the velocity when it's 1 inch from the center. So velocity, or 2 inches, excuse me, 2 times 7,200 pi. And I think a decimal would be more appropriate here. Oh my goodness. Okay, so it is 45238.9 inches per minute. Now if you wanted to convert that to inches per second, you would just divide it by 60. Now if I'm trying to calculate the velocity for 1 inch from the center, well, we could either just divide that by 2 or just do 7,200 pi on our calculator. That comes out to 22619.47 inches per minute. And again, if you'd rather have inches per second, just divide it by 60. Okay, sorry for the messiness, but that is our lesson.